All right, so this is the Unit 6 test. So for number one, write the cube root of 7 to the 8th power using rational exponents. So remember, the number here is going to stay as the numerator in our new exponent. So we're going to put 8 on top. The number inside the index is going to become the denominator. And I guess I should do a different color for 7, but the base stays as the base. So we just kind of write that, and then we're all set. So again, it's just a rewrite. So we just have to remember the little number that's the index is going to become the denominator. And this number right here is going to become the numerator. It'll stay as the numerator. That's it. Rational just means fraction. For number two, we got to solve this equation. So since we've got these two sixes and they're multiplying together, we can add these two fractions up. So 2x over 5 plus x over 3. We have 6 to both sides equals 6 to the 22nd. And now, since both of these two both of these bases are the same number, they're both 6's, we can cancel the 6's out. So we have the equation 2x over 5 plus x over 3 equals 22. Now from here, we just have to solve the equation, just like we did all the way back in Unit 1. We can see that these two denominators are not the same, so I have to get common denominators. So I'm going to pick 15, because that's 5 times 3. So 5 times 3 would get me 15, so I need to do the top also times 3. So, oops. So 2 times 3 would be 6x. To get from 3 to 15, I'd have to do 3 times 5 to get to 15. So 5 times x is 5x, and that's going to be equal to still 22. So now that the two denominators are the same, I can just add the tops. Remember, when we add fractions, we don't add the bottoms together. We don't add the denominators. They just stay as 15. 6x's plus 5x's is 11x's. So I get 11x equals 11x over 15 equals 22. I have to undo the 15, so I'm going to multiply both sides by 15. So I get 11x equals, that'll be 3330. And then since I'm multiplying by 11, I have to divide both sides by 11. So I'm going to get x equals, that's going to be, it's like 30. There we go. And that's it. So there we go. Again, kind of tough to solve this one, but once we transform it into just our fraction equation, that's a pretty nice equation that we can solve. So that's what we got for number 2. All right, for number 3, we got another solve. So we got 1/4 2 plus x equals 1/64 to the x minus 2. So I can see here that the 64 is the bigger one, so I'm going to leave the 1/4 alone. Oops, actually, I misspoke. We're going to go the opposite way. The 1/4 is the smaller one. Yeah, let's go that way. 1/4 is the smaller one. We'll leave that one alone. So we get 2 plus x. So I need to turn 64 into 2. So I have to think about powers of 4, because that's what I have over here. So 4 to the first is 4. So that's not the right choice. 4 to the second is 16. That's not the right choice. 4 to the third is 64. So that's what we want. So this is 1/4 to the third, because 4 to the third would be 64. And this is all still to the x minus 2. Now, when we have a power to a power to a power means we're allowed to multiply these together. So 1/4 2 plus x equals 1/4 3 times x minus 2. And now we're kind of in the same situation we were in from the last question, where now we got the 2 1/4 are the same. So since those 2 1/4 are the same, we can cancel them out. So that gives us 2 plus x, because that's what was over here, is equal to 3 parentheses x minus 2. Now here again, just like when we turned our exponential equation into the fraction one, here we turned it into a pretty quick equation. We can distribute the 3, so 2 plus x equals 3x minus 6. And now we're just trying to get the x by itself. So minus x both sides, 2 equals 2x minus 6, plus 6 both sides, 8 equals 2x, divide by 2 both sides, 4 equals x. And so we're all set. So that's what we got. All right, for number 4, an exponential function of the form f of x equals just b to the x. So in this case, a is like 1. And it includes the points 2, 36, 3, 216, and 4 comma 1296. We need to find the value of b. So to find the value of b, we have to remember b is what we're multiplying by. So if I look at my y values go from 36 to 216 to 1296. So I can think about that. And if I know the answer, I can just write the answer down. So if I know that this is times 6, I can just write down the answer is 6, and I can move on. If I didn't know the answer was 6, what we would do is we would take 2 of them and we would divide. We would do 216 divided by 36. But 216 divided by 36 is 6. And that's what gives us the 6. So b is what we're multiplying by. Multiply by 6 every time. For 5, we got another equation to solve. In this case, this one looks very complicated, but we can make it a little bit easier by getting rid of this fraction, because right now there's way too much going on here. So we're going to multiply both sides by 3 to the half to get rid of that 1/2 power down here. So that gives me 3, and again, I got power to a power, so I can multiply. So x over 2 equals, and 3, this is 3 to the first, so 1 plus 1/2 is 3 to the 1.5. So I did a whole bunch of exponent tricks there. So again, the exponent tricks I did power to a power means I'm allowed to multiply. But we saw that one already. That would be right here. Power to a power is multiply. And the other exponent trick I did is I added them up if I have the same base. So 1 plus 1/2, just like over here. When I have these as both 6s, I can add these 2 up. So that's the 2 rules that we did. And now, just like the others, this one actually ends up being really easy, because when the 3's go away, I get x over 2 equals 1.5. Well, I'll just multiply by 2 both sides to get rid of the 2. And x is also 3. It's already done. So even though that one looks like it's the scariest one, it actually turns out to be the quickest one. All right, for number 6, we have to identify all the key features. So we did pretty good with this before. In y-intercept, we can just plug 0 in. 8 to the 0th power is 1. The asymptote, since we're not adding or subtracting anything, is y equals 0. The domain of all exponential functions is all real numbers. And we're above the y-axis, or above the x-axis, so we have to do y is greater than 0. I'll graph it, though. You don't need to graph it, but we can graph it to check it out. So I didn't bring up Desmos yet. So if we graph it, we'll see the same thing. So we type it in, we get 8 to the power of x. And again, we can see we've got all those same ideas. If I type in what I picked for my asymptote, y is equal to 0, we can see that it's resting right along that line. So that's how we know that that's got to be the asymptote. To get the y-intercept, again, I can click here to get to 0, 1. I could write that down also, but that's what we got. For number 7, graph 3 to the x and its asymptote. So we can see here, looks like we're counting up by 3s because it's 6, 12, and 18. So I'm just going to draw on my other lines here. It's 15. These lines are all 1s. So it looks like I want to do -1, 0, 1, 2, so on and so forth. So for the x's, it looks like I want to pick -1, 0, 1, 2, 3, 4, 5. Maybe I'll go out to 6. We'll see. But f of x is going to be 3 to the x. So 3 to the -1 is 1/3. So we can plot that. That's like way down here. 3 to the 0 is 1. So that's still kind of down there. 3 to the 1 is 3. So now we're already up to this line. 3 to the 2nd power is 9. So I'll go right there. 3 to the 3rd power is 27, and so we're already going to be off the screen. So 18, this is 21. So I can estimate to be like way up here. So I don't even need to do those ones. I can just draw the curve in at this point. So draw a curve. So I go all the way up. I'll go all the way over. And so that's my graph. So I did the graph. Now I have to do the asymptote. So I have to graph the asymptote. A lot of people didn't graph the asymptote on the quiz. The asymptote is at y equals 0, so you just draw in the y equals 0 line. That's it. So this one, just like on the quiz, you actually have to draw the dots somewhat decently. You can't just put a swoop down and then call it a day, because a swoop doesn't do just 3 to the x, it just does something to the x. So you have to be very accurate in what points you're actually plotting. So that is the actual graph of 3 to the x, not some other exponential. Again, if you just wanted to graph it, you could graph it as well. So let's get rid of 8 to the x. And let's do 3 to the x. Now again, we get the graph. Can't just copy the curve down and call it a day again. What you got to do is double check the points. So you can make the table, gear, and then the table. And you can see, all right, these are the points that I actually need to plot on the graph in order to make it look nice. Otherwise, if it looks wrong, if it looks off, it's going to be wrong. For 8, write the exponential function for the set of points. So the exponential function is our equation that we've been using, y equals a times b to the x. You can use the f of x version if you want. A is always the starting value. So in this case, a is going to be 8. B is what we multiply by, so times 1.5 every time. And again, if we didn't know or if we forgot, we could just take two of them that are next to each other and divide. 27 divided by 18 is 1.5. X stays as x, y stays as y. And this is a pretty quick question if you know what you're doing. So there we go. All right. For number 9, so Joel has saved $60. He triples the amount he saves each week. So part A, does this represent an exponential function? So for our exponential function, remember the idea behind an exponential function is, are we multiplying? Because multiplying every time is the sign of an exponential. So I come up here, I see the word triples. Triples means times 3, so yeah, I would say yes it is. And that's what I would give as my justification. Triples is multiplying by 3 every time. That's our definition for an exponential, if we multiply by the same amount every time. Now I have to write the function that fits Joel's situation. So again, if it is exponential, we're going to do y equals a times b to the x power. He's starting with $60. So Joel's only got $60 at first, but he's going to multiply his money by 3 every week. And so there we go. So since we're multiplying by 3, 3 is going to be b. For number 10, population of a town is 4,000 and it grows at a rate of 2.5% per year. We need the approximate population in 10 years. So we're going to use our equation, y equals a times b to the x. The reason we're going to do it is we see that we've got a percentage here, and those percentage ones are usually going to be the exponentials. Starting amount, we got 4,000 to start. And then for the rate, we see it's going to grow. So remember, when it grows, that's our 1 plus the decimal. So 2.5% is 2.5 over 100. So 0.025. A lot of people on the quiz didn't convert that correctly, and so they lost points just because they didn't convert their decimals. They didn't convert their percentages into decimals. You have to make sure you actually do it. Again, there are no hints because the hint is literally right here. It says divide by 2 zeros. We literally divide by 100. So we also have one more piece. It says the population in 10 years, so we could just throw a 10 right there. And from this point on, it's just straight up calculator work. So we do 4,000, 1 plus 0.025 to the power of 10. So 5120. Again, you can round up or round down. We just want an approximation, so any sort of number that's close would be good. So there we go. For number 11, Sarah invests $3,500 at an interest rate of 3.3 compounded quarterly. How much is the investment worth at the end of 5 years? So again, we just start out with y equals a times b to the x. And we realize, okay, well, we're starting with 3,500. So 3,500 is our a. For the b, we're going to invest our money. So that means our money is going to grow. So we need to do the growth version. So 1 plus 0.033. This time, though, it's going quarterly. So compounded quarterly means that n is going to be 4. So we divide by 4. And then we go 4, and n in this case, our t is going to be 5 years. So again, we can develop it that way. If we want, we could just throw everything into the other equation, not y equals. Amount is equal to principal, 1 plus the rate over the number of divisions to the power of the number of divisions times time. So again, if you want, you can see I've got all the same things. P is the starting amount, 1 plus R, so R is our rate, N is the number of divisions, and then T is our time. So again, if I didn't want to plug them in, starting from y equals a times b to the x, if I wanted to just use the equation, I can just use the equation and get to the same place. Otherwise, it's just calculator work from here, so we're just going to throw in the calculator. So 3,500, 1 plus point, I forget what the decimal is, it is 033. 033 over 4 to the power of, parentheses, 4 times 10. I think it was 10 years. Nope, only 5 years. All right, so there we go. We got our value. Since it's money, we want to do dollars and cents. So 45.08, 41, 4125.08. That's it. So we got it. So that's what she got. So she's got an extra $625.08 after 5 years. All right, that's it with 11. All right, for 12, population of the fennec fox is 100,000. It's decreasing at a rate of 12% per year. In about how many years will the population be fewer than 50,000? All right, so let's see. We want to get our population right now, so we're going to use the equation y equals a times b to the x. We see we've got 100,000 to start with. So we'll put 100,000 in for the a. For b, because it says it's decreasing, this is going to be the 1 minus version. So we're going to do 1 minus the rate. So 1 minus 0.12. And we're going to go to the x power. Now this one, it wants to know in how many years will the population be fewer than 50,000? So it's checking for y. They want to know when that's going to be 50,000. Now, we can't really plug it in over there into the other equation and get a good answer because we don't really know how to solve it yet. But what we could do is we could graph it and see where those two things cross. So that's what we're going to do. So we're going to graph y equals 50,000. Let's get rid of all of these graphs. So we got y equals 50,000. And then for the other one, it's y equals 100,000 to start with. 1 minus 0.12 to the x power. All right, and again, nothing pops up, but we expect that because we were starting at 100,000 foxes. So we got to bring our y-axis all the way up a little bit past 100,000. So let's go 200,000. So there we go. We see we get a very nice looking graph. And we just come down here where they connect. So they connect at 5.422. I'm going to save this just in case the screenshot breaks again. Simple screenshots. That didn't work. Screenshot again. Lost my dot. We'll screenshot one more time. All right, and let's hope. All right, looks like we're good. So there we go. So again, we got our answer. So it'll be about 5.4 years. Now again, a decimal number of years is fine. That seems pretty good. Our other option is, since we put it into Desmos, we could do like we did last time and make the table. So we could go with the gear and then make the little table. And then we see, all right, at 2, we're still above, so that doesn't count. At 3, we're still above, so that doesn't count. At 4, we're still above, so that doesn't count. At 5, we're still above, so that doesn't count. At 6, we've gotten under, so we know that it'll be between 5 and 6 years. And this way would also be correct. So you could also do that with the estimations using the points. Here you might want to press enter, and instead of doing 7, type in 5.5 to see if it's closer to 5 or 6. And it looks like it's really close to 5.5. But again, that's what we kind of found. We found that it was about 5.4. So that's what we got for number 12. For 13, there are 3,200 bacteria in the lab dish. Population decreases by 3% per day. Compare the decrease in the population for days 1 to 3 with the decrease from 4 to 6. To do that, we just complete the sentence with more quickly, less quickly, or same rate. So let's get our equation set up. We're going to use the equation y equals a times b to the x. Probably not a surprise at this point. So what are we starting with? 3,200. In this case, we're decreasing. So decrease is the 1 minus. And we got 3% is 0.03. It's not 0.3. You got to actually convert it correctly. And then we go to the x. So we're going to throw that in. 3,200, 1 minus 0.03 to the x. We're going to get rid of these. 3,200, 1 minus 0.03 to the x. And again, that doesn't really look very good. So if I go home, I can still see I got nothing. But this time my target's around 3,200. So I'm going to pick a number that's bigger than that. So maybe, I don't know, 4,000. That seems decent. All right, so it still doesn't look great, but that's okay, because what we're comparing is from 1 to 3 versus 4 to 6. So if I look at the graph, it's kind of hard to tell. 1 to 3 versus 4 to 6, it kind of looks like it's the same. That might just be misleading because it kind of just looks like a line, but I know it's not a line. So what are we going to do? Hit the gear, make the table, and say I want to go from 1 to 3 and from 4 to 6. So I've got some of my dots. Let's get rid of the other ones that I don't want. So I got to figure out if that line is steeper than that line. So let's see. If we got 1 to 3, we can see the difference. So from 1 to 3, we're going to subtract them. 3104 minus 2920 is about 184. So we're losing 184 in 3 days. 3 minus, I guess it's only 2 days. That was not the right button. Divide by 3 minus 1. So we're losing about 92 per day. All right, if I go from 4 to 6, actually goes backwards. Got my Y1s, my Y2s mixed up. There we go. We're losing 92 a day. If I go with the other one, I've got 2832, so about 2833, minus 2666. See, we got 167 bacteria, but we're going from 4 to 6. And so we see we're losing 83 per day. So again, even though it looks about the same, that's just because my scale is a bit off. If I fix my scale, if I get really close to these numbers, and I don't go down to negative 73, I go to 2,500. Now all of a sudden it's a little bit more pronounced. We can see, yeah, this is a little bit less steep than this one. So it turns out our rate is increasing at a faster rate. So if we come down here, let me grab all my stuff. Doesn't look good. So I've got all of my data here. I don't have all my data because I missed the 2 other parts that I needed. So let's go back and grab those 2 parts that we definitely need. We definitely need those parts. All right. Size them up so that they go together. All right. So if I look negative 92 versus negative 83.5, so in this case, the population is going to decrease more quickly from 1 to 3. Because we're losing 92 versus losing 83.5. So since 92 is bigger than 83.5, the population is decreasing more quickly. And that makes sense because, again, with our exponential, we lose a lot at the beginning and then we flatten out if it's decay. So that makes a lot of sense. We actually didn't need to do any of this work if we just remember, well, a decay function, because this is a decay because it's decreasing, almost turned it into increasing. But since that's decreasing, we know the overall shape looks like that. And we are very steep here, and we're not as steep over at the end. So we could just answer that right away without doing any of the work if we know the idea behind the curve. All right, for 14, for the sequence 6, 18, 54, 162, we got to find out if it's a geometric sequence. So again, for a geometric sequence, it counts if it is multiplying every time. Remember, dividing counts as multiplying. So we just got to check. So how do I go from 6 to 18 times 3? 18 to 54 times 3. 54 to 162 times 3. So the answer is yes. And the reason is we're multiplying by 3. It's a really bad 3. We're multiplying by 3 every time. Now, if you wanted to double check, if you weren't sure, if you didn't see that was times 3, that's okay. What you would do is you would just check each of the pairs. So 162 over 54 is equal to 3. 54 over 18 is equal to 3. 18 over 6 is equal to 3. And since they're all the same, since they're all 3, then yes, it is geometric, and we're multiplying by 3 every time. For 15, we've got a new sequence. So for the sequence, we have to give the explicit formula. So remember, explicit formula is going to be A1 is going to be equal to some number. Oops, that's a recursive formula. Don't remember that one. So for explicit formula, that's the one that is A sub n is equal to A sub 1 times r to the n minus 1 power. Recursive formula is the one that's A sub 1 equals some number. And then we've got A sub n plus 1 equals A sub n just times r. So all we got to do is just fill in the parts that we've got. So for the first one, we can find A sub 1. A sub 1 is going to be 12. So I can start this off by saying A sub n equals 12. And I can start the other one off by saying A1 equals 12. R is what I'm multiplying by. So to go from 12 to 6, I'm multiplying by a half because I'm getting a half every time. So R is going to be a half. Down here, to make R a half, we say A to the n plus 1 equals A sub n times a half. And now for n minus 1, we really don't have anything because it didn't tell us to plug any numbers in for n, so we just leave it as n minus 1. And then both of those are done. So we're all set. Those two are very similar. So as long as you remember the formulas, they're pretty easy. Nice thing is this formula is super nice. It's just a times b to the x, same equation that we've had all the other times. This one is just write down what you start at and remember that you're multiplying every time. That's it with that one too. So that's it with 15. For 16, we have the explicit formula. We need to get the recursive formula. So again, recursive formula is A1 is equal to some number. And then A sub n plus 1 is equal to A sub n times r. So A1 is equal to, so to get our starting value, remember the starting value just is the first number that we've got out here, 37. We can see we did the same thing. So those were both 12. Now these are both 37. And at the bottom, A sub n plus 1 equals A sub n times 4.5. And again, we can see that's the same. Those two are the same thing. And that's it. We're done. So again, we just want to get the formula. That's the formula. For 17, now we have the recursive. We got to go backwards. So again, our formula to get to explicit is A sub n equals A sub 1 times r to the n minus 1. All right, well, A sub 1 is what we start with. Just tells us right there we're starting at 56. R is what we're multiplying by. We see the multiplication here of 7, 7. And again, we're not plugging anything in for the n, so we just leave it as n minus 1. And that one's done too. So just have to convert those two. Again, very nice, and seems like we did pretty good with those. For 18, how does 2x plus 8 differ from 2 to the x? Well, we got the little 8 on the outside. 8 on the outside means, oh, these are not right. These all need to be 8s. So 8 on the outside means that we got to go up 8. So we're going up 8. So there we go. If we want to double check, we can double check. We can just throw them in. So if we throw in 2 to the x, and then 2 to the x plus 8, we need to go back home because we're zoomed way out right now. We don't see the purple one, but that's because the purple one is hiding 8 above. So here we can see we're starting at 1. Now we're starting at 9. So it moved up 8. So that's the whole idea. Just know that that outside is the up and down. All right. For 19, we got x plus 5, and these are also not right. These need to be 5s. All right, so we've got 2 to the x plus 5. So we're in the parentheses, so we know we're going to go left or right. We're backwards, we're in the parentheses, so a plus sign is going to move it to the left. So we're going to go with C. Again, we can double check. We got 2 to the x. This time it's 2 to the x plus 5. X plus 5. And so we can see again, if we follow this point, we get 0, 1. I can follow it all the way over here to 5. So negative 5, 1. So we went to the left 5. And that's it. That's all there is with number 19. And then number 20, g is a transformation of f of x of 2x. Find the transformation for g of x from f of x. So we know that we're starting at f of x is 2 to the x. So, I mean, I know that we're starting with this graph. So it tells me, well, we've got some extra points. We've got all these points. I could plug them in, but before I do that, what I'm going to do is just make my table really quick, since I've got 2 to the x. And I'm going from 0 to 4, so I need a couple more. So I got 1, 2, 4, 8, 16. So I'm just going to plug those into my little hint table. Oops. 1, 2, 4, 8, 16. And now what it's telling me is, all right, if I need to go from f to get to g, I have to get from 1 to negative 4, 2 to negative 3, 4 to negative 1, 8 to 3, and 16 to 11. So what I'm going to do is take these two numbers and just do 16 minus 11 for 5. And so I have to add, oops, not add 5, wrong way. I have to subtract 5 to get back to here. So I guess I want to do this the other way to make it a little bit easier on us. Because we want to go 11 minus 16 is negative 5. So if I take whatever answers I have for f, if I just do minus 5, I'll get the answers for g. And that's it. So that's kind of the idea. And then we have to compare the graphs, select all that apply. So now that I know what the function is, I know that it's f of x minus 5. That means I know that g of x is equal to 2 to the x minus 5, because we just subtract 5 if we want to do minus 5 like that. So I'm going to plug this in, and I'm going to look at it and just answer the question. So 2 to the x minus 5. All right, let's go back home. And so it looks like pretty solid. If I want to double check my answer for part A, I'll make the table and see, all right, yeah, negative 4, negative 3, negative 1, 3, and 11. Okay, those are the ones that I should get. So it seems reasonable. So same domain. Well, all these exponentials have the same domain. They always have all real numbers. But again, if you want to check, all the way to the left, all the way to the left, all the way to the right, all the way to the right. So that's good. Same slope. So let's see. Same slope. Well, let's see. It doesn't look like we're changing the slope because we just moved it. we just moved it down. So it should have the same slope. Because again, we're going up by the same amount each time. So here, like I'm going from 1 to 2. That's a difference of 1. Here I'm going from -4 to -3. That's the same also. So yeah, because if we were to do the slope formula, if we were to do y2 minus y1 over x2 minus x1, like, I mean, we can tell the x's are the same, so I just have to check. 2 minus 1 is 1, -3 minus -4 is 1. 8 to 6, 16 minus 8 is 8, 11 minus 3 is 8. So yeah, the slopes actually are the same. That's kind of a weird one. Same range. Well, that one's definitely wrong. That's definitely out. So they can't be the same range because one is above the other one. So f of x, the range here, is our typical y is greater than 0. But since I move this one down, the range is y is greater than -5. So that's out. Same y-intercept, also that's definitely out too. If I look here, that one's got -4. That one's got 1, so they don't have the same y-intercept either. So kind of cool. They got the same slope, and they do have the same domain because all the exponentials have the same domain. All right, so that's it with this test. It's not really too crazy. Again, we saw a lot of it was just knowing that y equals a times b to the x. It seems like we need a little bit of extra practice with the exponentials. So we may need to work on some of these ones for all the equation solving that we have up here. But I think once you get past the equation solving, I think once you get past question 6, I think we're in pretty good shape because we've been doing pretty well with these ones in class, and we did pretty well with these types of questions on the quiz. So I think the challenge is going to be to get through questions 1 to 5. Well, most people do well with this one, so 2 to 5. So that should be a pretty big focus.